Hello, welcome viewers. Let's continue our topic about the relations. Just we discussed previous what is the relation and how we generate a relation. Now we see the different types of the relations. Here number one, it is reflexive. Say reflexive. Reflexive means, let us say X belongs to A. A is the given set. A is the given set and X is any element. X belongs to A implies X comma X belongs to R. What is R? R is the relation under the given condition. Simultaneously, we consider a numerical problem in this way set that say we have the relation say R is equal to 1, 1, set A is equal to 1, 2, 3, 1, 1, 2, 3, 1, 3, 2, 2, 3, 1, 3, 3. That is any relation, say, defined under rule R with the help of the set A. What does it mean? Let us see, if 1 belong to, here we see 1 belong to the set A. Let's see, 1 comma 1 belongs to the relation R. Yes, it belongs to this. If we consider 2, then 2 comma 2 also belongs to R. If we consider 3, then 3 comma 3 also belongs to R. If it is so, then it is reflexive. Then it is reflexive. Otherwise, not. Who? R is reflexive. Therefore, R is reflexive. Then we say symmetric. For symmetric, we require the two members of the set. Let us say X comma Y belong to the given set. Then X comma Y belongs to R. This implies Y comma X must belong to R. If it is so, therefore R is symmetric. R is symmetric. Let us see in this example, we consider any element say 2, 3. Here we say 2, 3 belongs to R, but 3, 2 does not belong to R. 3, 2 is there. So we can say it is not symmetric. It is not symmetric. Third property, it is transitive. It is transitive. For transitive, we require the three elements of the set X, Y, Z belongs to the given set. This is X, Y belongs to R, Y, Z belongs to R. This implies X, Z belongs to R. If it is so, then R is transitive. If any relation follow all these property, we call that relation is an equivalence relation. That is equivalence relation. If we see in this example, here it is 2, 3, here 3, 1, 2, 3, 2, 1. Number 3, we say 2, 3 belong to R, 3, 1 belong to R, but 2, 1 do not belong to R. Therefore, this relation is not an equivalence relation, rather it is reflexive, but not symmetric, but not transitive. So these are the main three properties for a relation: reflexive, symmetric and the transitive. If a relation follows all these three properties, then we say it is equivalence relation, otherwise not. Here we consider fourth property, that is the antisymmetric property of a relation, that is different from the relation equivalence. Say, what is antisymmetric? For antisymmetric, we repeat the same property like this. It means for antisymmetric, a relation should be first symmetric. If it is the property, we repeat again, let x comma y belongs to A, then x comma y belongs to R. This implies y comma x belongs to R. That we know it is symmetric. And this implies x is equal to y. If x is equal to y, then R is anti-symmetric. Then R is anti-symmetric. These are the four properties. We can discuss them with the certain examples. Let us see, first of all, let us consider the set of all the straight lines. Let us consider the set of all the straight lines and take the relation parallel. Let us say, let A is set of all the lines L is such that L is straight line, and relation R is like this, L1, L2 are two lines such that L1 is parallel to L2. It is the given conditions. Now we have to check either this relation is equivalence or not. For equivalence, we have to check all the three properties. Say, first of all, we check reflexive. For reflexive, we consider only one member, that is L1, say belong to A. No. Can any line be parallel to itself? Yes. According to the geometry, what we consider, every line is parallel to itself. So we can write, this implies L1 is parallel to L1. This implies L1 comma L1 belongs to R. Therefore, R is reflexive. R is reflexive. Number two, symmetric. Here, symmetric. For symmetric, we consider two lines, L1 comma L2 belongs to A. Here we see there are one is red line and one is black line. If red is parallel to black, then black is parallel to red. It means it is symmetric. L1 parallel to L2. This implies L1 comma L2 belongs to R. This implies L2 is parallel to L1. This implies L2 comma L1 belongs to R. Therefore, R is symmetric. R is symmetric. Now, third property, that is transitive. For transitive, we require three members. We consider three lines, say L1, L2, L3 belongs to A. If we say this blue line is parallel to black line and black line is parallel to red line, it means red line is parallel to blue line. If blue line is parallel to black, black is parallel to red, it means blue is parallel to red. It means the relation is also transitive. L1 parallel to L2. This implies L1, L2 belongs to relation R. L2 parallel to L3. This implies L2, L3 belongs to R. This implies L1 is parallel to L3, that is L1, L3 parallel to belongs to R. Therefore, R is transitive. R is transitive, or we can say R is equivalence relation. R is equivalence relation. What's about the fourth property? That is the antisymmetric. For antisymmetric, we consider the symmetric property again. Here, it is symmetric. L1 is parallel to L2. L1 is parallel to L2. This implies L2 is parallel to L1. What does it mean? But L1 is not equal to L2. Rather, both are the straight lines. Both are the straight lines. But they cannot be equal. Why? We have taken only the set of the straight lines. A straight line may be of 5 centimeter, other may be of 10 centimeter, 15 centimeter, 2 centimeters. We have not considered here L is the set of all the straight line whose length are 10 centimeter. If it was so, then it was a antisymmetric relation. No, it is not antisymmetric because the length of the both lines that may be the different. That's how we check the equivalence relation in a theoretical manner. Similarly, if we consider the same problem by taking the relation perpendicular, then again we proceed reflexive. For reflexive, we consider single line. In geometry, we consider every line is parallel to itself, but it is not possible if a line is either parallel or it is perpendicular. A line cannot be perpendicular to itself. Then L1 is not perpendicular to L2. Therefore, L1 does not belong to R. Therefore, R is not reflexive. It does not mean that we leave the problem here. It is not equivalence. We will have to check all the three properties. Second, symmetric. For symmetric, we require two lines. L1, L2 belongs to A. L1 perpendicular to L2. This implies L1, L2 belongs to R. A simple relation say this black line is perpendicular to red, then this red is perpendicular to black. It means it is symmetric. This implies L2 is perpendicular to L1. This implies L1 belongs to R. Therefore, R is symmetric. Now, for transitive, we require three members of the set, say L1, L2, L3 belongs to A. Again, we consider it with an example. Let us see this blue line. This blue line is perpendicular to red, and this black line is perpendicular to blue. But here we see if it is the position, then the black line is parallel to the red, not perpendicular. If this is perpendicular to this and this is perpendicular to this, if we combine, it means black is parallel to red. It means the relation is not transitive. L1 is perpendicular to L2. This implies L2 belongs to R. L2 perpendicular to L3. This implies L3 belongs to R. But L1 is not perpendicular to L2. we can say L1, L3 do not belong to R, therefore R is not transitive. It is neither reflexive nor transitive, but it is symmetric. That's the way we discuss about the theoretical problems by considering the examples. Similarly, we can create a relation, say in a family relation, we define a relation brother. We say there are 4 brothers in a family A, B, C, D. In logics, what we consider, every person is brother of itself. It means if A belongs to the family, then A, A also belongs to family, because A is brother of A. If we say symmetric property, if A is brother of B, then B is also brother of A. It is symmetric. And what's about transitive? A is brother of B and B is brother of C. This implies A is brother of C. It means it is transitive. Therefore, this relation is equivalence. What's about its antisymmetric property? A is brother of B and B is brother of A. Rather, it is symmetric. But we can't say A is equal to B. Both have the different personalities. A is different and B is different. So we can't say both are same. It is an antisymmetric property for the example. In the same manner, we can consider, say, a relation of father in a family. Let us say the father, a husband, their children, 2 boys, 2 girls. Let us consider a family. No. For reflexive, we consider a person, father. No one is father of itself. It is not reflexive. If we say A is father and X is son, if A is father and X is son, if A is father of X, then X is not father of A. Because X is son of A, it is also not symmetric. Similarly, it is also not transitive. In this way, we can consider the theoretical examples. Let us consider some more example on this. Consider the set. Let set A is equal to 2, 3, 4, and here a relation is given. Say R is equal to 2, 3, 4, 2, 4, 4. First of all, for reflexive, we require only one member. Say, consider any member. We say 3 belongs to A. Let us say 3. Here it is 3, 3 belongs to R. Therefore, R is reflexive. What's about the symmetric? That is, we need 2 members. Say 2, 3 belongs to A. It is 2, 3. See, 2, 3 belongs to relation R. What's about 3, 2? But there is nowhere 3, 2. 3, 2 does not belong to R. Therefore, R is not symmetric. And what's about the transitive? Here we see transitive. 3 members, 2, 3, 4 belongs to given set A. We see 2, 3 belongs to the relation, then 2, 3, 4 belongs to the relation, And what's about 2, 4? What's about 2, 4? It also exists in the relation. 2, 4 also belongs to R. Therefore, R is transitive. R is transitive. Then this way we can check the properties reflexive and symmetric and transitive and anti-symmetric. No. We can represent these properties in the form of the matrix like this. Let us see. If we consider the same example, here is the same example. It is, we can write it into the matrix form like this. Here we write 2, 3, 4, then again 2, 3, 4. Now we see 2, 2. 2 to belong, we write 1. If that which pair exists for that, we write 1, and which pair is absent for that, we write 0. 2, 3, here it is present, we write 1. 2, 4, we write for 1. 3, 2, there is no 3, 2, we write it 0. 3, 3, we write it 1. 3, 4, we write it 1. Then 4, 2, not present, it is 0. 4, 3, not present, it is 0. 4, 4, it is present, it is 1. Simple. Those pairs, ordered pairs which are present, we represent them by 1, and those which are absent, we represent them by 0. And if we remove this and the remaining, we can convert it into the matrix like this, into the matrix form. If the relation is given in the matrix form, we will have to check their properties in the same situation. How? Let us name these elements A11, A12, A13, first row, first column, first row, second column, first row, third column, A21, A22, A23, A31, A32, A33. First of all, how we check the property reflexive? Here, reflexive, we see A11 is equal to A22 is equal to A33 and that is equal to 1. If all the diagonal elements are same, it does not mean if all the 3 are 0, we say reflexive. No, they must be 1. If all the elements, diagonal elements are 1, we say reflexive. For symmetric, we select any member who is present in the relation. Say A23. Here A23 is equal to 1. Now we see what's about A32. A32, it is 0. It is 0. Therefore, it is not symmetric. Not symmetric. What's about transitive? Let us consider say A13 is equal to 1, A32 is equal to 0, A13 is equal to 1, A32 is equal to 0. It is not transitive. Or we can consider A12 and A23. This second example say we consider A12 is equal to 1, A23 is equal to 1. Then what's about A13? A13 again that is equal to 1. It means it is transitive. Therefore, R is transitive. In that way, we can convert a relation into the matrix form, and again we can check the same properties, reflexive, symmetric and transitive, or we can convert a matrix relation into the ordered pairs relation. That's about the relations. Now, next topic we shall discuss about the functions. Before that, we understand about some intervals. Say, there are two types of intervals. We write that closed interval. How we present closed interval? Closed interval by these brackets, or we can write it that is equal to x belongs to R such that x lies between A and B. It means A and B are also included. Then open interval we represented by this. It means x belongs to R such that x is strictly between A and B. It means we do not count the values of A and B. For example, if we take, say, x lies between 3 and 6, this implies x is equal to 3, 4, 5 and 6. Second, if we consider x is strictly between 3 and 6, then we cannot consider 3 and 6. We say x has only two values, 4 and 5. That is the difference between the open and the closed interval. If it is like this, it means it is from one side closed and from other side it is open. For example, that is, say, from 2 to plus infinity. 2 to plus infinity. Here it is closed and up to infinity it is open. In this way we can represent the functions or intervals. So, know about the functions. Let us understand function is just, we can say it is also an image, maybe the image of a relation. For understanding the relation, let us consider these are the two sets. Let us say A and B. Both A and B, they belongs to N. N is the set of the natural numbers. N is the set of the natural numbers. Now, we define a relation from A to B. Say it is square. Say it is square. It means every element in A has its square in B. 1 square 1, 2 square 4, 3 square 9, 4 square 16, 5 square 25, 6 square 36. These all are natural numbers and these are also all natural numbers. If we say in this way, every member in A has its square in B. That is a function. We can represent it in this way. F is a function from A to B. Before writing that, we understand it in this way that someone is standing in front of the looking mirror. He can see his image. If there are 2 persons, there will be 2 images. If there are 3 persons, there will be 3 images. If there are 4 persons, there will be 4 images. If it is so, every person has its own image, then it is a function. Then it is a function. But we can't say the person is one and it has the 2 images in the mirror. It means it is not a function. Or we can say a person is standing in front of the mirror, but there is no image. Again, it is not a function. Here we have considered the example, every natural number in A has its image. If we consider it is a mirror, its image in B. So we define this set as codomain. This set as codomain and this set as domain. And these elements, they are called pre-images. Pre-images means objects standing in front of mirror. And these elements, they are called images. And elements of this set we denote if denoted by y, and these elements if we denote by x, then we define the function f from a to b such that y is equal to x square. It is a function. It means every member in codomain, is square of the every member in the domain. Or we can say each image in the codomain is the square of pre-image in the domain. That is the function. That is, if we can write it in this way, 1, 1, 1, then 2, 4, 3, 9, 4, 16, 5, 25, and this. It is a function. Then what's about this? If we consider some, say, other example like this, f is equal to, say, 1, 1, 1, 1, 2, 4, 3, 9, 4, 4, 5, 25. What we can say about this? We say no, it is not a function, because here 2 also has the image 4 and 4 also has the image 4. It means two different persons have the same image in the mirror. That is not possible. So we say it is not a function. First of all, we have to see how to identify the given function is really a function or not a function. In this way, we see each member must have the separate image. Each member must have the separate image in the codomain. If it repeats, then we say it is not the function. Now let us consider about its properties. First of all, we say 1-1 mapping, 1-1 mapping or 1-1 correspondence. 1-1 correspondence. 1-1 correspondence means simply it must be a function. If each pre-image, these are all are pre-image. If each pre-image in the domain has its unique image in the codomain, then we say it is 1-1. If each pre-image in domain have unique image in then we say it is 1, 1. Then we say it 1, 1. Or we can say algebraically x1, x2 belongs to the given set, say A, then f of x1 is equal to f of x2. This implies x1 must be equal to x2. The case we consider this example, here we see it is a 1-1 correspondence or 1-1 mapping, because every member has the unique image in the codomain. 3 cannot have image 4 because the square of 3 is 9. 5 cannot have the image 9. Why? 5 is the image of 5 is, that is 25. So it is the example of the 1-1 correspondence or 1-1 mapping. Then what's about the onto? Again we see in this example, say onto. For onto, what we do? No, we check from inside the mirror. Say inside the mirror there are images. If there are images, then that image must have at least one object in front of the mirror. If object is not present, then the image will not exist. Or we can say, if the image is existing, it means it has some object in front of this. That object we call the pre-image here. Or we can say every image in the codomain must have at least one pre-image in the domain. It means if every image in codomain, have at least one pre-image in domain, that we have written here at least. It is mathematics, rather it is in physics we say only one object, one image. Or we can say one image, that's one object. But in mathematics there may be the difference, or there is the difference in the law. Here we see the same example. First of all, say it is the set of the natural numbers and B is also the set of the natural numbers. It means for onto, what we consider, now we look from inside the mirror, outside the mirror. From inside the mirror, outside the mirror. It means from here we find x is equal to under root y. It is mirror, no, it is pre-image. X is equal to under root y. Let us start counting. Under root of 1, 1. Under root of 4, 2. Under root of 9, 3. It seems that every image has its pre-image. But see, 2, it is also natural number. Here, 3 is also natural number. 5 is also natural number. 6 is also natural number. 7 is also natural number. If they can come here, they can come here also. They are also natural number. No. We see what will be the image of 2. Image of 2 will be according to this relation, that is under root 2. Image of 3, under root 3. Image of 7, under root 7. That is a contradiction, because it is the set of the natural numbers and these rational numbers cannot live in this set. So we say this relation is 1-1, but it is not onto. If a function is both 1-1 and onto, then we say it is bijective. We call this property injective, this property surjective. and if both exist, then we say it is bijective. Then we say it is bijective. Let us discuss some other more example. Say, we say take the function y is equal to modulus of x. Y is equal to modulus of x. These are the particular examples. Modulus means we count always positive. Let us again draw our diagram like this. Where we say x comma y belongs to R, word of real numbers. It is word of real numbers. First we see 1-1 correspondence. 1-1 correspondence, or we call it injective property. Y is equal to modulus of x. It means if we take the value of the x, modulus of 1, that may be positive 1 or that may be minus 1. Because modulus of both these numbers is this, again positive. Or we can say, if consider the member 1, here the function is modulus, then 1 in front of plus 1 and minus 1. It means similarly 2 have 2 images, plus 2 plus minus 3, 3 plus 3 minus 3. It means every member has more than one image. Every member has more than one image, so we can't say it is 1-1. It is not 1-1 correspondence because 1 has more than one images. Now what's about the onto? For onto, we see from the mirror, from inside the mirror. The pre-image of plus, say it is also, the pre-image of plus is again 1 and pre-image of minus 1 is again 1. It means every image has at least one pre-image in the domain. So we can say it is onto, but it is not 1-1. Let us consider some more examples from this. If y is equal to, if A is equal to R minus 3, R is the set of the real numbers, and B is equal to R minus 1. It means from the part of real numbers, 3 is deleted, from the real numbers, the 1 is deleted. And f is a function defined from A to B such that the function f of x is equal to x minus 2 divided by x minus 3. We have to check either it is bijective or not. If it is bijective, it means if it is injective and surjective, then we say it is bijective. If it is bijective, then it is invertible. We add one more line, then it is invertible. If it is invertible, it means its inverse exists. Let's try find out here. First of all, say 1-1 mapping, about 1-1 mapping. Here function is f of x is this. We say let x1, x2 are the two members belonging to the world of real numbers. Then what is f of x1? That is equal to x1 minus 2 divided by x1 minus 3, and f of x2 is equal to x2 minus 2 divided by x2 minus 3. According to definition, f of x1 is equal to f of x2. It means x1 minus 2 divided by x1 minus 3 is equal to x2 minus 2 divided by x2 minus 3. If cross multiply them, x1 minus 2 into x2 minus 3 is equal to x1 minus 3 into x2 minus 2. If we expand it, x1, x2 minus 3x1 minus 2x2 plus 6 is equal to x1, x2 minus 2x1 minus 3x2 plus 6. That is, if we solve this problem, we get x1 is equal to x2. If it is so, therefore we say f is injective. F is injective. Or we say f is one-one correspondent. And for onto, we consider from inside the mirror. It means it is y. If y is equal to x minus 2 upon x minus 3, cross multiply xy minus 3y is equal to x minus 2, xy minus x is equal to 3y minus 2, x y minus 1 is equal to 3y minus 2, then x is equal to 3y minus 2 upon y minus 1. And here we write let y belongs to R. If y is a real number, it is also a real number, it also belongs to R. So we say function is surjective. Function is surjective. If a function is surjective and injective, then we conclude f is bijective. F is bijective. If f is bijective, therefore f is invertible. F is invertible. Therefore, its inverse exists. And what is that? Then f inverse is equal to, that is the same value which we found here, calculated here. F inverse is equal to 3y minus 2 divided by y minus 1. That is the complete approach of this function regarding our concept. Then we see the further some few properties of the function. All the functions, they follow the rules of the algebra, plus, minus, division, in the same manner as we follow in a simple algebra. It has some particular property, say, that is the composition. Composition does not mean multiply. Let us consider, say, there are the two functions, f of x is equal to 2x square plus 2x plus 3 and gx is equal to 3x plus 5. We can add them, we can subtract them, we can divide them. No. What is the difference? No, it is the property composition. It is the property composition. We write it this F composition G. O stands for composition. F composition G for X. It means that is equal to F of, follow the rules like this, F of Gx. F of Gx. That is equal to F of, what is Gx? Gx is 3x plus 5. What does it mean? Replace every x of f by 3x plus 5. It is 3x plus 5 whole square plus 2 into 3x plus 5 plus 3. No. Similarly, we can find G composition f with respect to x. That is G f of x. We follow the definition. G, what is f of x? 2x square plus 2x plus 3. No, we replace every x of g with this. It is 3 into 2x square plus 2x plus 3 plus 5. Now that is called the composition of the two functions. Composition does not mean multiply. Let us consider some more examples. Say f of x is equal to log x and gx is equal to e raised to the power x. So first of all, we find f composition g. That is f of g x. It means f of what is gx? That is e raised to the power x. That is log of e raised to the power x. That is x into log e, and that is equal to x. Log e is equal to 1. Now we try to find out g composition f. That is g f of x. That is g log x into e. It is e raised to the power log x, and that is equal to x. Therefore, we can write gf is equal to f. We can, in short, we can write also in this way. Sometimes this composition may be equal, sometimes may not be equal. We can represent any function in the form of the permutations like this. These are permutations of the function. Here, say there is a function a1, a2, a3 and so on. An are the objects standing in front of the mirror, and fa1, fa2, fa3, fan are their images in the mirror according to the rule f. So if we write the function in this form, we call it a permutation also. That is permutation. Permutation, simply we write first object and below that its image. Object, image, object, image, object, image. So we discuss about its properties. Some say, let us consider, say f is the 1, 2, 3, 2, 3, 1 and g is equal to 1, 2, 3, 2, 1, 3. These are the two functions in the form of permutation. Again, we can find f composition g. F composition g. That is equal to, no. Difference is here, in place of x we have the numbers. In place of x we have the numbers. F of g. For this we start with this. F of g1. Here g1. What is the image of 1? In g, that is equal to, image is 2. No, 1 in f we see image of 2 is 3. That is equal to 3. So we can write f composition g is equal to, objects will remain always same, 1 to 3. F composition g means image of 1 is 2 and here image of 2 is 3. We write 3 below 1. For second element, it is f of g2. We write f of g2 means 1. F of 1. And in f, image of 1 is 2. Then we write 2 under 2. Again, we will find f of third element g3. There g3, image of 3 is 3. Image of 3 is 3. Then f3, here image of 3 is 1. That is equal to, it is f composition g. in the form of the permutation. Similarly, we can find G composition F. G composition F. Now we will start from F. Here G F of 1. G F of 1. In F, the image of 1 is 2. In F, the image of 1 is 2. And in G, image of 2 is 1. And if we write the composition 1, 2, 3, it is 1. It is G F. So second element G F of second element 2. Here image of 2 is 3, G 3, and in G image of 3 is 3. Now for third element G F of 3, G F of 3, that is, what is F of 3? G in F image of 3 is 1, and in G image of 1 is 2. That is equal to 2. That is F composition G and G composition F in the form of a permutation. The difference is, here are 3 members, they may be 4, 5 or 6. We find them image of the image, image of the image. Let us see. In the simple formation, if we consider, say, F is equal to 1, 2, 3, 4, 5, 6, 4, 5, 6, 3, 1, 2, and G is equal to 1, 2, 3, 4, 5, 6, and it's 5, 6, 4, 2, 1, 3. Simply, we find here F composition G. F composition G. We start from G. First of all, write the objects 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. So we, as G, we start from G. In G, image of 1 is 5. In G, image of 1 is 5. And in F, image of 5 is 1. So we write 1 under 1. In G, 2 has the image 6, and here 6 has the image 2. So we write 2. Here, image of 3 is 4. Here, image of 4 is again 3. Image of 4 is 2. Here, image of 2 is 5. Here, image of 5 is 1. And here, 1 has the image 4. 6 has the image 3, and 3 has the image 6. It is F composition G. If we are going to find, secondly, G composition F, we write the first line as it is 1, 2, 3, 4, 5, 6. Because the objects will remain same. No, we will start counting from F. We consider the permutation at the last. Now, if start from the 1, here 1 has the image 4, here the 4 has the image 5, result is 5. 2 has image 5, 5 has image 4, 3 has image 6, 6 has image 6, 4 has image 3, here 3 has image 1 has image 4, and here 4 has image 2. 2 has image 5, and 5 has image 1. 3 has image 6 and 6 has image 3. 4 has image 3 and 3 has image 4. Here 5 has image 1 and 1 has image 5. Here 6 has image 2 and 2 has image 6. That is F composition G and G composition F. So third step we see represent. We can represent F as product of transpositions. F as the product of transposition. To find the product of transposition, we select the cycle in the given permutation. Say here permutation is F. Now we select the cycle here. 1 has the image 4, 4 has image 3, 3 has image 6, 6 has image 2, 2 has image 5 and 5 has image 1. Here we started, here we terminated the cycle. Then we write it in this way. 1, 4, 1 has image 4, 4, 3, 6, 2, 5 and don't repeat the 1. After that cycle, we split it into the transpositions like this. 1, 4, 1, 3, 1, 6, 1, 2, 1, 5. It is called the product of transposition. Product of transposition. As we found in the F, similarly we can found in any permutation. Say in G, we see 1, 5, 5, 1. It is very small. 1, 5, finish. If we see in this 1, 1, here it finishes in GF 1, 2, 2, 1. So F has the largest cycle. We start counting 1, 4, 4, 3, 3, 6, 6, 2, 2, 5, 5, 1 and again we stop because we started from same number and terminating number is same. And if we write in this form, that is a product of transposition. If we count them, say 1, 2, 3, 4, 5. 5 is odd, we say transposition are odd. If their counting is even, we say the transpositions are even. That was regarding the functions. Now, any question up to this, which we discussed today? If you have some problem, you can want to ask any question regarding this topic, any confusion, any point, you can ask. It is a totally theoretical topic which we were discussing. You know, it will be some troublesome for you, but it is not so typical as often the students take it. It's only the matter of understanding with concentration or with the examples. Any question, viewers? Anyhow, thanks and good day.